All right, recording has started, so good afternoon, everyone. Today we're going to be covering section 3.3. So let me just briefly give some context of where we're at and where we're going. So far, in section 1, we kind of just reviewed some pre-calculus principles, or section 1, not section 1, but chapter 1. Chapter 2, we started to kind of move in the direction of what is a derivative, right? We defined it in this way as the instantaneous rate of change or the slope of the tangent line, these sorts of things, right? And then I keep saying section when I mean to say chapter. Chapter 3 is all about these shortcuts for derivatives, right? So we learn these rules on how to find derivatives based on the function. So far we learned, 7 rules, right? Okay, so let me quickly recap what those were, just before we start. So those rules were the derivative of a constant. Okay, so if we do a derivative of just a number, we just get 0, right? The next step up from a constant is, okay, what if the function is changing a little bit, but at least it's changing in a constant way, right? Well, if the rate of change is constant, then the instantaneous rate of change anywhere is going to be the same, right? It's just going to be whatever the rate of change is of that function, which for a linear function has a constant rate of change. So its derivative is a constant, right? And that constant is just the slope of the linear function. Okay, then we learned the derivative of a sum or a difference, right? So this was a really special rule. Okay, and what I mean when I say that it's special is that for the derivative of a sum or a difference, we found out that actually the derivative of the sum of two functions is the same as just the sum of the two derivatives, right? And the reason I say that this rule is special is because a similar rule is not going to be true for the derivative of a product of two functions, or of a quotient of two functions, or of a composition of two functions, right? So this is the only time where we can just say, oh, just kind of distribute, as it were, the derivative, right? Okay. So then we also learned the derivative of a constant times a function is really just an extension of this sum rule, which says, well, if I want to do the derivative of a constant times a function, it's just the constant, whatever that constant is, times the derivative of that function. Okay, that just comes from the fact that multiplication is nothing but repeated addition, right? Okay, any questions on the first 4 rules that we did there? All right, the next rules we learned were for a larger class of functions, right? So we said, okay, what if the function, oh, I forgot to cover the power rule. So the power rule said, okay, anytime I have a derivative of a function like x to the n, okay, so the independent variable is being raised to a power which is a number, right? Then the derivative of that is just going to be whatever the power was, we bring it down and multiply it in front, and we decrease the power by 1. Okay, so that was pretty simple. And then we practiced, combining all of these rules together, right? Oopsie. How about later? Okay, come on. There we go. All right. So next up we learned the derivative of some more complicated functions, like functions where the independent variable is in the exponent, right? What do we call functions where the independent variable is in the exponent? Very good, exponential. I think that was Shania. Good job. Okay, so exponential functions where the independent variable is in the exponent, we learned how to do those derivatives via these rules, okay? And that was where we kind of learned the easiest rule ever, which was how to do the derivative of something like e to the x. And the coolest thing about the number e is that if you take the function e to the x and you do its derivative, you get e to the x back, right? That's why we're interested in the number e, because that's a very surprising thing. You know, most of the time we take the derivative of a function, we get something different, right? Something maybe drastically different, right? Okay. And then the derivative of ln of x, right, is just 1 over x. Okay, so these are the rules that we learned so far, and we learned how to try to combine them all and do a bunch of derivatives. And we're going to continue learning more rules today. Actually, we're going to learn one more rule today, which is the chain rule, which tells us how to take the derivative of a composition of functions. Okay, so we're going to move to section 3.3. I know in the syllabus I said I was going to do section 3.4 first, but I changed my mind. I'm going to do section 3.3 first. So just to remind you, there's a homework assignment due tonight at midnight. There's also a quiz today in the last 15 minutes of class. Office hours from 3 to 4:30 today. Are you still having SI sessions for the rest of the week? Okay, SI sessions the rest of this week on Wednesday and Thursday from 6 to 6:50. Okay, any administrative business before we start for today? Okay, if not, then let's go ahead and get into it. So, if you recall, earlier in the semester, we had some of these problems. Okay, I want to focus on these warm-up problems for a second. We had some of these problems. I think we had one on the test, and we had one on a homework, and maybe we even had one on a quiz. I don't remember. But we had these problems about compositions of functions where we kind of flipped the script on the way we usually do these composition problems, okay? A lot of the time, what we do for composition problems is they say, okay, f of x is x squared, and g of x is x cubed, and they ask you, okay, what is f of g of x then going to be equal to, right? This is the normal way that we're used to seeing these composition problems, right? And we have to take one and plug it into the other, right? But in the flipped version of it, they're going to do the following. Instead of telling us what the functions are and asking us what is the composition, they're going to tell us what is the composition and ask us to go backwards and find out what are the functions, okay? And that's a more difficult problem to do, right? Okay, so let's just practice these first ones really quickly, and let's just do the first one together. So, what I'm told is that y is equal to f of z. Okay, so y is a function of z, and z is a function of t. Z equals g of t. Okay, and then y is going to be given by the composition of these two functions. Okay, so y is a function of z, but z is also a function of g of t. So if I replace z by g of t, then I get f of g of t. And so this is telling me that, this first part is telling me that if I take those two functions and I plug them into one another, then I get ln of 3 times t. So what I'm supposed to do is write down a function, f of z, and a function g of t, such that if I compose them in this way, I get this function. Okay? And in my opinion, for a problem like this, the easiest place to start is all the way on the inside. Okay? All the way on the inside. So I want to think about, well, if this function is one function being plugged into another function, I want to think about, well, what is the innermost function? Right? What is the innermost function? What's the function that's being plugged in? Right? So what do we think for this first one? What do we think about an inner function for this problem? Yeah, 3t, right? You can tell that it's the inner function really easily in this case because it's literally inside the parentheses, right? Okay, so if g of t is 3t, and if I plug 3t into the function f of z, and I get ln of 3t, then what then must have been f of z? Yeah, very good. ln of z. Okay, this is a tricky concept the first time you see it. So I expect that probably a lot of students have a little bit of doubts about this so far. How are we feeling? Let's have thumbs up for I feel good about this. Thumbs down for I'm not so sure. And then somewhere in the middle. If you're in the middle. Okay, cool. It's looking fairly good. Let's do another practice just to solidify that idea. Okay. So if okay, this is a good one because there's multiple ways that you can do this, right? Okay. So there's really two ways in which we could do this. Or maybe there's even more ways we could do this. I guess there are more ways that we could do this even than that. But let's just see if we can come up with some on our own. So f of z and g of t, right? So in this case, like I said, I always like to start with the function which is being plugged into another function. What do we think for this one? Could be the inner function. Adria?
2t plus 3.
Yeah, I think 2t plus 3 is a pretty natural choice. It's natural because it's inside the parentheses, right? So it's kind of like you think about when we compose functions, what we're supposed to do is quote unquote plug with parentheses. So you imagine if you plugged with parentheses that would be the function that you're plugging in, right? Oh yeah, sorry. I put it in the wrong spot. Thank you. Yeah, 2t plus 3 is going to be our g of t, which is the inside function, right? And then what's it being plugged into? Someone else help me maybe. Yeah, 5z squared, right? Thank you. Okay, so if we just take z and we replace it by 2t plus 3, then we get 5 times 2t plus 3 squared. Okay. Can anybody for brownie points tell me another way that I could have solved this problem that's not the same way? Does anybody see another way I could do this? Okay, what if I pick g of t to be 2t plus 3 squared? That's g of t. Then, if I take 2t plus 3 squared and I plug it in for z, in f of z, I get 5 times 2t plus 3 squared. What then must be f of z? 5z. Very good. Okay, so we're starting to recognize there might be multiple different ways of writing this down, right? Okay, but for our purposes, we're going to see today that the first way is a little bit better in this particular circumstance, okay? Because what we're going to learn today is how do I take the derivative of a function like this, right? And the rule which we're going to learn is going to relate the derivative of the composition of two functions to the derivative of each individual piece, right? So if we want to say the derivative of this composition is going to have something to do with those two derivatives, then we want these two derivatives to be, we want these two functions to be functions which we know how to take their derivative. And I can do the derivative of these two, but I have not yet learned how to do the derivative of something like this. Okay? So the first way is a little bit better in this circumstance, but we're going to see a ton of examples today, okay? All right, any questions on these composition problems? I know it's a little bit weird trying them for the first time, but I promise we're going to do so much chain rule, you're going to be able to do these in your sleep pretty soon, okay? All right. So what is the chain rule? We're gonna jump into it. Okay, you know what? Why don't we warm up with these problems really quickly? Just remember how to do the derivative of these functions, okay? So the first one, okay, I'm gonna need to use like 4 rules maybe. First of all, I see that I have a constant being multiplied by a function, so the constant multiple rule is definitely going to be in effect. I've also got an e to the x, so exponential rule is going to be in effect. I've got a constant, so the constant rule is going to be in effect. I have ln, so the ln rule is going to come into play. And finally, I have a sum of 3 different functions, so I know that the derivative is just going to be the sum of the derivative of each piece. Okay, so I'm going to have a plus and a plus. The 2 is going to hang out, and what's the derivative of ln? 1 over x, very good. And then 5 is going to hang out, and the derivative of e to the x is the easiest one you ever do, just e to the x. Okay, maybe it's the second easiest one you ever do, because what's the derivative of 2? 0. I don't know. It's up to you which one you think is easier. Okay, so that's pretty simple. Next one is just a straight up power rule, right? The 5 hangs out, and then what do we do with something like x cubed? We take the power, we multiply it down front, and then what do I do to the power? Decrease it by 1, so it goes to 2. Minus 2 times 2x to the 1, right? But if I have something to the 1 power, it's just itself. So I just write 2x. All right, so if you want to clean it up, it's 15x squared minus 4x, right? Okay, so that's that. So now let's learn about the chain rule. Okay, so the chain rule says, that the derivative of, so remember that, recall this notation here, just means the derivative of f of g of t is equal to, so what do? I have 2 functions one of them is being plugged into the other function. Well, the derivative of something like this is going to be equal to the following. F prime of g of t times g prime of t. Okay? So this is a tricky rule to get comfortable with. Okay? So I don't want anybody to beat themselves up if they don't immediately get this, okay? Because it takes a bit of practice to get this under your belt and start feeling good about it. Okay, so what does it say? It says, to do a derivative like this, first what I should do is identify what is f and what is g, right? And then what do I need to do? I need to take the derivative of f and plug in g, i.e. leave g alone, just do the derivative of the outer function. And then I need to multiply by the derivative of the inside function. Okay, so this is the process by which we do the chain rule. So let me show you a quick example. So if we want to do something like e to the 15x, okay, we already learned a rule actually which says what the derivative of this. So option 1 is to use the e to the kx rule, right, which says that the derivative of e to the kx is just k times e to the kx, right? So in this case, we would get y prime equals 15 e to the 15x, right? But option 2 is to recall that the derivative of e to the x is just itself, and use chain rule. So, if I want to use option number 2, here's the process. If I'm going to use the chain rule, I need to identify an inner and an outer function, okay? In this particular circumstance, anytime we have a power where the power is a function, okay, then you can kind of think of some imaginary parentheses up here and think of that power as your inner function. So g of x, okay, is going to be 15x, and f of x, why don't I say f of z is going to be just e to the x, right? Then, if I plug in 15x for, should have used z, sorry. If I plug in 15x for z in f of z, then I get e to the 15x, right? And these are two functions whose derivatives are really easy to do. In fact, let's do them. G prime of x, if g of x is 15x, is just 15, right? And f of z is equal to e to the z is the easiest derivative ever. It's just, again, e to the z. So by the rule, it tells us that the derivative, so I want to do the derivative of e to the 15x, which I know is the derivative of f of g of x, right? Which I know by the chain rule is f prime of g of x times g prime of x. And I know what f prime is, I know what g is, I know what g prime is. So all I'm going to do is plug them in. So the first thing I need to do is take regular g, so that's 15x. And what do I need to do? I need to plug it in for z in f prime of z. Okay? This is how I get this first term, okay? That's what I'm going to do. I'm going to take g, and I'm going to plug it in for z in f prime of z. So I just get e to the 15x. And now what do I need to do? So this part is corresponding to this guy. So that's when I just plug this guy in there, and I get e to the 15x. And now I have one more thing to do, which is to then multiply by the derivative of whatever g is. Well, g prime of x is 15, so I'm going to multiply this times 15. Okay, so this is the process for chain rule. Is first, take your function and identify an inner and an outer function whose derivative we know how to do. Then, find their derivative and apply the formula. Okay, the formula just says once I know what g and f and g prime and f prime are, it's as simple as plugging g into f prime and then multiplying by the derivative of g. Any questions about this first example? Okay, let's see another one. Let's work through this one together. I'll do it. Okay, so for this one I've got f of x equals 3x cubed minus x. Now there's two methods I could use to do this. If I were to FOIL, I could FOIL this 5 times, right? And then I'd get an expression which looks something like 3x to the 15 plus something x to the 14 plus something x to the 13 plus ... And then I could use the power rule like 15 times. But that's kind of annoying, right? We don't want to do that. So we can use the chain rule to make this a lot simpler. So what I want to do is identify an inside and an outside function whose derivatives I know how to do. Now, I've already used the letter f here, so I'm going to try to express this as maybe g of h of x, okay? Now, things are going to get a little confusing here with the letters, but what I want to illustrate here is what matters about the chain rule is not the letters f and g, okay? What matters about the chain rule is the form, okay? It says derivative of two functions being composed is derivative of the outside function, where we plug in the inside function, times the derivative of the inside function, okay? So if I use different letters, it's going to look slightly different, but that's okay. So if I want to express this as g of h of x, then h of x is my innermost function. What do we think for h of x? Yeah, I think that's a great option. 3x cubed minus x. Specifically, I think it's great since I can do the derivative of this using nothing but the power rule, the sum rule, and the multiplication by constant rule. Okay, and if that's my h of x, then what is g of z? Just z to the fifth. Good. And that's also great because I know how to do that derivative too. Okay, so let's go ahead and do the derivatives because I know I'm going to need them. H prime of x is 9x to the second power minus 1. Then g prime of z is 5 times z to the 4. We all good so far? Okay, now using this general form, okay, f derivative of a composition is equal to the derivative of the outer function where we plug in the inside function times the derivative of the inside function. What I want to do is apply that now to g of h of x. Using this form, how would I rewrite this in terms of g and h on the right-hand side? Very good. Does everybody see what Shania did there? All we're doing is using different letters, right? But the form is the same. Any questions about that part? Okay, so let's do it. Now we know what the formula is, so let's just do it. That's just gonna be, well, what do I need to do? Let's use the same colors. I need to take regular h and I need to plug it into g prime. So if I do that, I get 5 times 3x cubed minus x to the power 4 times the derivative of h, right? Which is just 9x squared minus 1, but I have to multiply by the whole thing, so I'm going to put that in parentheses, right? Okay, and I forgot to highlight this part. Yellow corresponds to this part here. Okay? So let me show you really quickly what this looks like. As you go forward, right, you do more and more chain rule, you're probably not going to always write out all of this stuff, okay? So let me show you really quickly what it looks like when you do it a little bit faster. Once you recognize, okay, this is the inside function and this is the outside function, you recognize what you need to do first is the derivative of the outside function, which in this case, the outside function is z to the fifth, right? So what you do is actually, in practice, you probably look at something like this and you see the 5 power and you say, aha, what I need to do if I want to take the derivative of something like this is I need to write first, leave the inside alone, 3x cubed minus x, and I am going to do 5 and then to the power 4, right? That's the derivative of the outside function where we leave the inside alone. And then what you need to do is take this inner part and multiply by its derivative. So, well, let me show you what that looks like if I were to do it the fast way. The fast way, okay? I would say the derivative of 3x cubed minus x to the fifth. What I need to do is derivative of the outside function where I leave the inside alone. So that's 5 times 3x cubed minus x. And now what I need to do is so-called chain rule out the derivative of this guy, which is 9x squared minus 1. And after a while, you'll start to recognize this pattern, and you'll be able to do it without writing out H and G or F and G or whatever letters you want to use, right? But it takes some time to get to that part. So I suggest first try practicing where we write it all out, and then once you get a hang of how this goes, you can start trying to do it the fast way, okay? All right, any questions on the first two problems? Okay, then we're going to spend about 10 minutes doing these kind of as a class, so we'll just work through them together. And then there's a little bit of group work, and then we'll have the quiz. Okay. So now we're going really to the big leagues, right? Not only do we have a function which we're going to have to do the derivative of using the chain rule, I've also got other functions being added on. But that's okay because I know that the derivative of a sum is just going to be the sum of the derivatives, right? So in this blank, I'm going to write the derivative of 7t squared. In this blank, I'm going to write the derivative of 9. And in this big blank, that's where the derivative of this guy is going to go, right? So we're taking it a step further now. So let's first just take a look at this guy. And first I want to mention, how we can tell whether or not we should use the chain rule, right? That's one thing that we should definitely know how to do. Even though we know how to use the chain rule, we should know when to use the chain rule, right? And for this first part, the reason that's jumping out at me that I should use the chain rule, okay, is I can see with my eyes, I see a function inside of another function, right? That makes me think these functions are being composed, which gets me to start thinking I should use chain rule. Okay, so that's the clue when we look at a problem. Okay? So from there, what we need to do is, of course, identify our inner and our outer function. So in this case, I've already used the letter F here, so why don't we go with G and H again? Or why don't I really go crazy? We'll use R and S. So we're going to do R of S of t here. R of S of t. So let's identify what is the inner function, S of t, going to be. Yeah, 2t squared plus 2. Very good. And that means, of course, that R of t must be what? Or, okay, why don't we use R of z? I've been going with a different variable here. That's technically the best way to do it. 5 ln of z. Very good. Okay, now I just need to find their derivatives. S prime is going to be 4t. And R prime of z, what's that one going to be? Yeah, 5 times 1 over z, or 5 over z. So then how do I get the derivative of the first part? Well, I know that the derivative of the first part by the chain rule is going to be R prime of S of t times S prime of t. And then I'm going to have to add on the derivative of the other part, right? Which, let me do that in blue. So, plus 7t squared, that derivative becomes what? 14t. And then how about 9? Just becomes 0. But I'm not going to write minus 0. I'm just going to write plus 14t. Okay, so now what I need to do is compute what this thing is, right? I already found out what S and R are. That was the hard part, right? And now then I found their derivatives, and now all I have to do is use this formula which I have memorized, right? And plug in. So derivative of the outside function first, where we plug in the inner function. So that's my R prime of S of t, and what does it look like? When I do it, I get 5 divided by, I replace z by s, which is 2t squared plus 2. Now I need to multiply. I need to multiply by s prime of t, which is the derivative of the inner function, which is just 4t squared. No, it's just 4t, sorry. Okay, and now, of course, I shouldn't forget that I need to add 14t, right? So that's how I would do the derivative of something like this. Okay, so again, I know that in my experience, a lot of students have struggled with understanding the chain rule when we use different letters, right? Like this time I'm using R and S. Last time I used G and H. The first time I used F and G, right? But it's circumstantial based on the problem. So in this problem, I didn't want to use F because F is already defined in this way, right? So if I said f of t is 2t squared plus 2, that would kind of contradict what this rule already told me what f is. So that would be sort of poor form. But you can use whatever letters you want. What you need to remember about this rule is the form, okay? And the form is basically derivative of the outside, where we plug in the regular inside, then multiply by the derivative of the inside. Okay? Any questions about this first one here? Yeah, Brendan.
So the expression outside of the two functions just hangs along to the right?
Yeah, exactly. So the rule that we're using here is that I have a sum, right? I have a sum and a difference. So on the first day of derivative rules, right, we learned that the derivative of a sum of two functions is just the sum of the derivatives, right? So in this case, if I do the derivative of these three things being added and subtracted, what I'm actually going to get is just first whatever the derivative of this thing is, and then plus whatever the derivative of this thing is, and then plus whatever the derivative of this thing is, right? It just so happens that in order to compute the derivative of the first thing, we have to use our new rule. Does that answer your question? So yes, in other words, the other stuff does just kind of hang along for the ride, but we have to do its derivative, of course, right? Okay, great. Any other questions on this first one? That was a great question. All right, let's see another example then. Okay, we got now P. Oh God, it's not even P of x, it's just P is equal to 2e to the x squared plus 7 minus 5 ln of 2x minus 1. Okay, this one looks tough. All right, well, since we're given the equation in terms of p and not in terms of p of x, I'm going to solve this using Leibniz notation. So what I want to do now is write down what is the derivative of p with respect to x. So the way I write that using Leibniz notation is just dp dx. Okay, so this is the symbol for the derivative of p, which is what I'm going for. And now on the right hand side, what I need to write down is whatever the derivative of this expression is. Well, I've got two things being minused, right? So I know what I can do by the difference rule is just write down whatever the derivative is of 2e to the x squared plus 7, and then subtract whatever the derivative is of 5 ln of 2x minus 1. Okay, that's the difference rule. And I guess diff here is kind of ambiguous. You might think it's differentiation. Difference rule. I guess sum or difference rule. Okay, so that's what I need to do. So let's start with the first one. What rules am I going to need to use to take the derivative of a function like 2e to the x squared plus 7? Let's see if we can list them all off. I think I see like 4 rules. You can give me one of them. The power rule I am going to need to use for the x squared, right? I am also going to need to use the chain rule, right? How can I tell that I should use the chain rule for this problem? Adria?
There's a function inside of a function.
Function inside of a function. All right, so that's 2 rules so far. I think I have 2 more rules to go. E to the x rule. So 2 more rules after that, in fact. Just focusing on the first part for now. Sorry?
Times something.
Constant multiple times something. And then the last rule, it has to do with when actually two more rules. Yeah, derivative of a constant, and then one more rule, which is the derivative of a sum, right? Is the sum of the derivatives. Because I'm going to need to use that for x squared plus 7. Okay, so this is the idea that I want everybody to be going through when they first see this thing, is think about what rules am I going to need to apply here? And, once you've got an idea of that, you can sort of start moving forward. Okay, so I know it's a composition of functions, so I want to identify what is the inner function and what is the outer function in this case. So if this is f of g of x, then what's g of x? Yeah, x squared plus 7. I like using the inner function is just whatever's in the power in this case, right? And f of z could be 2e to the z. Does everybody see how we got those? Would anybody like a little more careful explanation of how we got those? Okay, let's just go through it really quickly. So, what I want to identify is I want to set it up like this. Okay, the reason I want to write it like this is because I don't have any rules which tell me how to do the derivative of something like this. This is too complicated for me to just go ahead and do the derivative just like right off the bat. So what I need to do is use the chain rule here, and the tip-off is that I see x squared plus 7 inside the power. So you can kind of think of there being some hanging parentheses here, right? And if you think of those hanging parentheses on the left and right of x squared plus 7, it's kind of like that's a function being plugged into another function. Okay, if you see a function in a power like this, then whatever function is in the power is going to be your inner function. Okay, so that's how I determined what g of x was. And once I had g of x, I know that if I plug this into f, I get 2e to the x squared plus 7. So if g of x is x squared plus 7, it's kind of like taking the place of whatever's here, right? So that's how I define the z here, is just 2e to the z, so that when I plug in and I replace z by x squared plus 7, I get what I had initially. Okay, so now I need to move forward and actually do the derivative of that thing. So if I want to do that, I need to know what is g prime. Well, it's just 2x. And what is f prime? Well, it's just 2e to the z. So what I need to write now is f prime of g of z times g prime of z. Okay, which is going to be equal to 2e to the x squared plus 7 times 2x. Okay, now for the other part. Actually, before we move on to the other part, everybody clear with how we got this being the derivative of this? Or still a little confused? Okay, let's. How about the other derivative? Do I need to use the chain rule for this one? Yes. Why? Yeah, function inside of a function. So if I have a function inside of a function, what's the inside function? If this is, why don't we use r of s again? R of s of x. Then the inner function, s of x, is 2x minus 1. How do I know that? It's because it's inside the parentheses. It's furthest inside. R of z is then going to be 5 ln of z. S prime is then going to be equal to 2, and r prime is going to be equal to 5 over z. Now what I need to write is minus, right? So this minus comes from here. And now I need to write down what is the derivative of this thing, which by the chain rule should be r prime of s of x times s prime of x, which looks like 5 over 2x minus 1 times 2. And now I'm done. Okay, so in this case, we had to use the chain rule for two different functions. But since they were being subtracted, we know, we just take them piece by piece. Okay, start with the first function. I use the chain rule on that. Once I got the derivative of that bad boy, I just move on to the other bad boy or bad girl. I don't know. So we want to. Wow, that's too gender normative because I use blue and pink too. Sorry. Okay, so what are we doing here? We just take the derivative of each piece individually. We got to use the chain rule for each one. Are there any questions on how I did this one? Or how we did this one? Okay. I'm going to show you one more example of how I might do this a little bit faster, and then we'll have 10 minutes of group work. Okay, so let me show you the fast method. And this is only really to be used once you have a better understanding of the chain rule, but once you get the hang of it, you start to see how this thing works, okay? The way it works is I can clearly see there's a composition of functions here. I can clearly see that the inner function is going to be this q squared plus 1, right? And then the outer function is just going to be, okay, the inner is q squared plus 1, and the outer is just going to be ln of z, right? So when I do it the fast way, what I just remember about the chain rule is what I should do is, the first thing I should do is just treat the inside as just z, and then just do the derivative of whatever the outer function is. So in that case, I just get 1 divided by q squared plus 1, right? That'd be what I would do if I just did the derivative of ln of q squared plus 1 if q squared plus 1 was just a number. But it's not just a number, so what I need to do now is multiply by the derivative of that inner function, which is 2q plus 1. Just 2q, sorry. Okay, so for the fast method, I get there pretty quick, but it necessitates a pretty strong working understanding of how the chain rule works in terms of the form, right? So start with the f and the g and writing out the f prime and the g prime, and then f prime of g of x times g prime of x, right? But after you get the hang of it, you'll be able to do this in this kind of faster way. And we'll do this more going forward. I'll show some more examples further in class. Okay, any questions on this one? All right, let's get together in groups for just a second. We're going to work on a bit of a more high cognitive task, and then we're going to do our quiz. Okay, so for 10 minutes, we're going to get into our groups here and try out this problem, which is pretty tricky, okay? We've got to find derivatives of compositions of functions based on the graph of each of those two functions. All right, so let's get into a group and try this one out. If you finish up early, you can move on to the next problem if you want.
This way makes a little bit more sense. The only thing is, whenever it's hard to pick out the inner and the outer ones, but
Like where they meet. I really did the whole page.
I think that's where you're supposed to start. You're not gonna have it's the same sort of thing that we were doing, kind of derivative of like pi. But at first you can pick up the equation because all they give you is the graphic number that gives you like p's, which is like the equation. But instead you just graph it. So you kind of have to pick out what g of x is equal to f of x and off of the graph. And from there you do a little bit of so and then f of g of x.
Yeah, that's one way to do it. I was thinking to start by just defining each prime of x and then we're doing this one. With the chain rule for that. So like, 2x, but then plus and then find the values.
Find g of x at 1. Right, so I'm going to write that. 7, right? So, okay. And then find f prime of 7.
That's what I was thinking.
That's what I told 7. And it's, okay, so
Yeah, I think
oh, I thought you meant.
they both equal, like, one time of your
So, find this when
Each of one is f of g of y.
Well, they both times.
exactly. Well, first of all, we're going to be able to identify what it is.
Yeah, then I guess you can find those
Well,
values
it's
on the
easy.
graph.
All I do is I go where but I need to good, so we got negative 2 points, right? One, adding g of x, and then we get f prime at 7, and we got 2. Okay, how do you get f prime at 7? That was so at 7. So, if you look at 7 and f prime, oh, you know, it's also 0. Yeah, we're looking at the slope, right?
That would make sense.
So what else? Yeah, so it would be 0. Then it doesn't really matter with the multiplier. You guys are on the right track, right? What we're trying to do here is use this formula, right? For h prime 1, we just replace h prime by f prime of p of x times h prime change both sides. No, okay. So let's think about this. We want to find h prime 1, right? Okay. So h prime of x since it's the composition of that result. So if we want to do h prime of 1, what we're really interested in doing is what happens if we put a 1 here and a 1 here. Yeah, that's oh, so right. Do you see what I mean? I don't care if you go into I think we like just be the answer with exactly. But if we plug in 1, right, for the g of x, right, what we need to do is just check what is the height of the function. When x is equal to how do I figure out what is G prime of one? They went I can find out what is G prime of one. I was thinking so. What is the parameter to tell us about the function? So this one, so if you want to find out what is G prime of one, what we want to know is what is the slope of the G function when x is equal to 1. No, it's not. Yeah, it's like negative ones, right? Because it's not a linear function, so it's got a constant rate of change, right?
Okay, let's come back together really quickly. Yeah, let's go ahead and straighten our desks out. And then we'll chat about this really quickly before we do the quiz. Okay. So I saw a lot of good work out there. Let's just really quickly recap what we're supposed to do here. So the first thing to check is, well, we want to know what is h prime of 1, right? What is the slope of the h function when x is equal to 1? But the thing is, we're given the graphs of f and g, but not the graph of h. But we are told that h has a relationship to f and g, right? h of x is equal to f of g of x. So we know, for example, that h prime of x is going to be equal to, because of the chain rule, f prime of g of x times g prime of x. So that's just a chain rule. And my goal is to find out what is this thing when I plug in 1. Well, I know it's equal to the other thing on the right-hand side, so if I plug in 1 on the left-hand side, it's the same thing as plugging in 1 on the right-hand side, right? So h prime of 1 would just be equal to f prime of g of 1 times g prime of 1. So in order to find out what this is numerically, we just need to check, well, g of 1 is nothing but what is the height of the function when x is equal to 1. So that's this height shown here in red, which is 7, right? So that's g of 1. So this is the same as f prime of 7 times, and now the way I figure out what is g prime of 1, of course g prime is nothing but the slope of the function, which, since this g function is a linear function, if I were to draw a tangent line here, it would just be the actual line that we are on, right? And if I ask myself what is the slope of that line, it is -1, right? Because we're going down at a rate of 1 unit. Our rise is -1 and our run is 1, right? So this is f prime of 7 times -1. But of course, to do f prime of 7, all we need to do is then check what is the slope of the f function when x is equal to 7. So we're looking at what is the slope of the tangent line here. So again, that one looks like its slope when x is equal to 7 is 0. So this is actually going to be equal to 0 times -1, which is just 0. Any questions on that one? Is that a little bit more clear now? Sorry. Yeah, Christian?
What did you do, what did you do at the very end when you went to 0 is equal to, 0 times -1? After you got f prime of 7 times -1, then what was the next step?
So the next step is to plug 7 into the f prime function, right? The f prime function, what does it do? It tells us, you give me an x value, I'll tell you the slope of the function at that x value. So I go to the x value, x equals 7. It can be seen here. And I check, what is the function doing when x is equal to 7? It's going straight across, right? as it's going straight across, what is its slope in this moment?
0.
0. So that's how I got 0 there. Good question. Any other questions? Okay. We're going to see a lot more chain rule moving forward, okay? So the key to learning this stuff is practice, practice, practice. I'll post some homework at some point for you. And, all right, yeah, we're going to start the quiz now. So please clear your desks. Except for a pencil. You can use a calculator if you want, but it won't help you, I don't think, on this problem. Or on this quiz. If you have an Apple Watch or another smart kind of device anywhere on your body, please take it off and put it in your backpack. Notes go away, everything goes away. Please keep this face down until everyone has a width. All right, everybody has a quiz. Everyone's stuff is away. You may begin.